All right, so let's talk about support vector machines. We're going to talk about them, various versions of them. So a support vector machine is a very simple machine learning model, and it can perform linear and nonlinear classification, regression, which is fitting data to points, and novelty detection, but it doesn't scale to large data sets. Now, linear SVMs are the simplest and most common type, and what this does, if you have two groups of data, like you have the yellow dots and the blue dots, any of these lines would do. I see Isaiah asking, how long will the videos remain? They should stay up forever. They'll just go on my old classes page. So let me just mention this. This is a frequently asked question and an important one. Right now, they're all on the pages you reach from here. After this class is over, you click old classes, and all my old stuff is up there. So the videos will stay up as long as YouTube leaves them up, which should be forever, I suppose. Anyway, so if you wanted to separate these two, you could use this red line and get 100% success, or this purple line, and you would get 100% success. So what is the best line? And in support vector machines, you do this. You choose a line that has the biggest margin. So this would be the best line. And that, of course, makes sense because if you imagine these are just samples and there's going to be some noise, then you'd like to have the widest possible margin. So the strange thing about this, though, is this is only defined by these two dots. All the rest of them don't matter. These are what's called the support vectors, and this is a support vector machine. It doesn't matter what these are as long as they're on the right side. It's only the ones on the edge that completely determine which line is best, which is very strange. But that's true for support vector machines if you have the original kind that requires 100% success. So adding more instances won't affect the boundary. You add more blue ones over here, it doesn't change the answer at all. That's what's strange about support vector machines. So if you have dots that are completely isolated, which we're going to do in the projects, then of course you can make a support vector machine that will completely separate those dots. But it's sensitive to scaling. So suppose you change the scale of the y-axis. So this goes by ones and this goes by hundreds. Now, the optimal support vector machine is like this, because remember, it wants to make the road wide, and this scale is much more important than that scale. So missing them by what looks like a tiny amount here is the widest road. And that's why I mentioned, and we've gone into it many times, that if the data is not scaled carefully, your your machine learning models can end up doing bad things. So this is called hard margin classification. Even if you have an outlier here, the line moves way over there to avoid it, and you can't solve it at all in this case. If your outlier is actually in the wrong group, then there's no line that will 100% work. So you don't usually use this hard margin support vector machine. What you use is soft margin, where you allow some errors, and you have a regularization hyperparameter here, which allows how much, and now more than just those two dots are determining it. And if you make a low C for hypersaturation, that makes the street larger with more margin violations, which are ones that are not separated, and you have more instances supporting the street. So you can move from the hard one to degrees of softness in this decision. So there's another project to work. I think it's still part of the same project there. You can see here's one with a regularization parameter that is too far from the optimal, so it totally fails. The line is off the map and everything is interpreted as blue. Here's a better choice where it draws a better line through these points. So even though there are some margin violations, ones that are on the wrong side, you make a reasonable line to separate with some degree of accuracy the reds from the blues. Now, what if you can't use a straight line? Well, you could add features like with only X1, you can't separate the green and blue dots. You need X1 and X2. Now you can separate the green and blue dots with a line here. And so this is just X1 squared. You can add a new parameter, as we've done before. So if you add polynomial features up to degree 3, then you're really fitting a straight line in a multivariate space that includes x squared and x cubed. But if you plot it here, it is a curve. And so now you can fit moons. Moons is a common automatically generated data set that has this property where the boundary between them is a curve to test your model. And as you can see, it did a pretty good job of fitting that curve with a polynomial of degree 3. There's also something called the kernel trick, which I don't fully understand, but there's a way to change the kernel at the heart of the calculation to reach the same result without actually calculating those extra dimensions. And it can be done in the software with this, but I can't tell you exactly how it works. It's a mathematical trick to make the calculation faster to get to the same place. So here's the polynomial kernel doing the same thing. A degree of 3 is the third order polynomial. You then go to degree of 10. And as you see, it's now able to make a more irregular curve and able to swing in here and such. And the end result looks pretty much the same. And you do have a couple of regularization parameters to determine what degree to use a polynomial and how many margin violations to tolerate. You see, there is some difference. Like this one miscategorizes this blue one. This one nips down and gets the blue one, so it's a better fit. All right, then you can measure. There's another way to do it with similarity features, where you can measure how much each instance resembles a landmark. So you have a landmark here and a landmark here, and you measure the distance to the landmark. This is another way to create a new variable, a new dimension, which you can use to make it easier to fit things. And there's something called the Gaussian RBF scalar that has the width of a Bell function and adds that sort of similarity feature to things. And the point of that is you can now try to fit this with the Gaussian RBF kernel. You're actually able to have boundaries like this, which is interesting, where only the things inside there are blue, and you'd interpret these as green. I think you probably don't want that, but you can see you can move through various things here. Here's the straight line fit, and with other regularization parameters, here you go to what's probably the best fit. Here you go to these more exotic fits. So you can have different solutions. And it's really a human judgment to decide which of these is really the best representative of the data. Is it really true that these blues are a little isolated region and everything out of it is green? In case of the petals, it's probably more this, that everything over here is one species and everything over there is another species. All right, and there's something called the string kernel, which uses the Levenshtein distance for text, which is the maximum number of single character edits required to change one word to another. This is a simple way to get the distance between words. And so, like I said, linear kernel is mostly what you use. These others you use only in more exotic situations. And so then you can consider time complexity. The linear support vector machines, M is the number of training instances, number of data you have, and N is the number of features. And so it's the product of them. These other ones, SVC is M squared times N, or M cubed times N. And this classifier is, again, N times N. So it's not, you can see that the support vector machine with the kernel gets more complicated. The kernel trick makes it more computationally expensive here for large data sets. So then we can talk about regression with support vector machines. So a classification was where you're trying to find a border to separate these two by minimizing the instances on the street. Regression is the opposite, where you want to put as many as possible on the street. You're trying to draw a line through the points. So it's sort of the opposite. This is regression. You're trying to find the line that captures the most possible instances within a reasonable width here. And epsilon is the width of the street. You can kernelize it so it can handle curves and fit curves through the data point. And so under the hood of these things, it's got a decision function is weights times x plus a bias is the prediction function here. This is where it predicts predicted values from all the x1, x2 to xn inputs. It can predict the output. It's just a linear combination of all those parameters. And you define the margin size here. So a smaller W means a wider margin. So here the margin is that wide, here the margin is that wide with W equals 1. And if you have a hard margin, then you want to keep instances off the street And that's a way to make a classifier here. I forget the details here. You're trying to make your decision function so it is greater than 1 for all positive instances and less than -1 for all negative instances, and never in the region 1 to -1. So you have a clear, empty street between the two categories. The soft margin is where you do allow instances to violate the margin, and here's the mathematical expression of that, where you're allowing a C, a regularization coefficient, to allow, you're minimizing something, but you are allowing some instances to be incorrectly predicted and tolerating some degree of that. And these variables determine how much margin violation you're allowed to tolerate. Then there's something called the dual problem, which is faster than the support vector machine problem and faster to solve when you have a large number of instances. This is what the kernel trick uses. And I don't pretend to understand the mathematics I just mentioned as you go along. That's the mathematical expression that justifies this kernel trick to get to the same place with less computation. And here's some kernels that are out there: linear, polynomial, Gaussian, and sigmoid. These are various ways to have curves built into your support vector machines. So that's the theory, such as it is. Let me stop this one. Well, the recording seems to have strangely moved. I got paused, but I don't have recording. Ah, there it is. Okay, good.